thank you for coming, the organizers for putting this on, and for the invitation for me to come. Thank you. I am a really, really strange guy. I work at the intersection of digital technologies and life science. It's been a fascinating journey for me, and I try and inspire others to find their path through digital technologies and bioscience by sharing some of the stories that of my life. So I just want to say right from the start, please look at me as an ambassador, not necessarily a scientist, not necessarily a businessman. I work at the intersection of these three areas: technology, all technology, including life science, business and how we grow enterprises, and stories, visions, because we need to be able to communicate and connect with the world. It's a very odd place to be because I'm not really a scientist, I'm not really a businessman, and I'm not really a storyteller, but it comes together in some pretty unique ways. Now, my burning question is, what will engineered humans look like? And I want to be clear, this is almost a taboo topic. It scares people. And this is why I want to go head on into this space with you. Now, we all know this technology. Digital technologies have invaded the world. Every area of society, every business, it's completely changed the way we live. We accept it. The cell phone, digital technologies, the idea of computation, data, and more than that, printing, turning data into real things, whether it's buildings or a 3D printed object. We're comfortable with this. But there was a digital technology that existed in a manufacturing technology before any of the stuff that we built. And it's life, and you just heard some of this with Floyd. These are living cells growing and dividing in time-lapse. And I want to be clear, this is the most advanced manufacturing technology on the planet. We have cells that are making thousands of different proteins in a regulated way, copying their genomes, one becoming 2 to 4, 8, 16, it's exponential. And human cells are billions of years more evolved than the bacterial cells here, but it works on the same machinery, the same code. Nature didn't fork the code. It took Floyd and his team to generate a new code. That's something really significant. This is technology that is still attributed to gods, but we've been dissecting it at a molecular level now for almost 100 years. Of course, you go into a cell and you pull out the DNA, you can sequence it, you can read it. It's a digital code, not ones and zeros, A's, T's, G's, C's, and now some X and Y's. But it's a digital code. We can read it. And reading DNA has become almost a universal pastime in life science. It's how we start to understand the machinery of life from the most basic level. This really catalyzed and expanded because of the Human Genome Project. It's the biggest project that was ever done in life science. It had a $3 billion budget, a 15-year timeline. And at the end of the day, what it did was not just unlock the human genome, but the genome of every organism on the planet. And it was sold to society as the potential to diagnose any human disease. The technology didn't stop when the Human Genome Project stopped. It was largely complete by 2000, and the finishing work was done by 2003. But the technology of reading DNA kept getting better and better. It tracked alongside Moore's Law for the next few years, and then suddenly we got this massive acceleration as new sequencing technology was developed. We've never had a technology grow this quickly. It's really strange. But the reason why it outpaced Moore's Law is because it's a universal code. And as people came on board and engineers came on board, it was this massive concentration of human creativity and engineering working to solve one problem. How do we read DNA faster? I've been obsessed by this chart. It shows the falling cost of DNA, but the growing value of the information we can get out of DNA. And that's just accelerated. Now we've passed an economic inflection point where by reading a human genome, we can get more value out of it than the cost of getting it. And just before I came here to Mexico, this company took the covers off. I advised them. It was founded by George Church and a couple of 20-year-old entrepreneurs. It's called Nebula, and what it basically does is make human genome sequencing free. You get to own your genome. It connects you to payers that will pay to read your genome just for the privilege of looking at it, and you get to keep all the data. So not only is reading a human genome free today, you can get paid. This opens up the potential to unlock all of humanity's treasures. We're all different. We all have a unique genome. And as we start to collect this information and analyze our millions, if not billions of genomes, our knowledge of life science explodes. And more than that, it's not just reading the human genome that's important. It's reading all genomes. You heard about microbial genome sequencing and prospecting. Well, this project caught my eye just a month ago. It actually wants to sequence every eukaryotic organism on the planet. That's every animal and every plant over the next 10 years because this technology has just become so cheap. This is a revolution. When will we sequence the last organism on Earth? It'll be this century. But writing DNA is even more powerful. That's when we start to engineer. That's when we start to create. This is Emily Leprouche. She's the CEO of a company called Twist Biosciences. They write DNA as a service. They IPO'd on Halloween. It's a remarkable deal. You can literally 3D print the DNA molecule now. And other companies are coming in to make even more powerful technologies all the time. This is just one based out of France that is now using enzymes, the same machinery that's in our cells to write DNA. This changes everything. Because just as Google was founded in a garage in the 1990s, now we can get biotech into the hands of almost everyone because you can write DNA digitally. All you need is a laptop. We're starting to see literally grade school bioengineering kits be sold. This is a company called Amino Lab, started by some friends of mine, and it comes with a handbook on how to do this. It's made for kids. We've seen thousands, almost 40,000 students go through an international program to learn how to program living cells. This is called the iGEM program. This was just a few weeks ago in Boston as they came together to share their work. It's spawned new biotech companies like Ginkgo Bioworks that design and build organisms to make high-value compounds. And also Zymergen, which is using the same technology to make thousands of new biomaterials. This isn't life science working at a bench. This is life science done by robots at an incredible scale and pace. But my interest is synthetic viruses, whole genomes. I want to be able to write entire genomes. The first one was done in 2002. Since then, only about 30 synthetic viruses have been made. I've been using this technology, making viruses that hunt down and kill cancer cells. It's a remarkable idea. We catch the flu, we get sick. If we design the virus, we can make only the cancer cells get sick. And it's also teaching us how we're going to defend ourselves against viruses, both natural and designed. This is a really powerful technology that is essentially design and build of the simplest living organisms. It offers the potential to make truly personalized medicines, because how much did your last cold cost you? A viral genome is incredibly small and easy to write today. We're moving beyond that. Craig Venter and his team in 2010 made the first designer bacterial cell. This isn't a synthetic cell in the sense that all the machinery and the code is natural, but it's simply, you just write the genome. And at the forefront of this, we're writing yeast genomes. This is the same yeast you use for bread and beer. This work will be wrapped up shortly, and it's important because yeast are closer to you and me than their bacterial cousins. Now, if you're writing DNA, the more you write, the more complex it gets. Today, writing proteins and viruses is fairly straightforward, or adding a metabolic circuit to a cell. If you're really well-funded, your company or your organization, you can start to think about making whole bacteria or yeast. But this work, being able to make large chromosomes of plants and animals, or potentially humans, that's still science fiction, that's the future, but it's coming extremely fast. This is why I had the pleasure of pulling together an incredible group of scientists over the last few years to make a new genome project. This time, not to read the human genome, but to learn how to write it. And not just the human genome, every large genome. We're doing this because we need to create a landing pad for this technology in society, because it's almost here. We need to understand the IP, the ethics. The ethics are extremely important, but also build open tools and technologies so it's not just the domain of a single company. GP-write in the last few years is a bottom-up project, and it's grown now to have over 1,000 participants and 100 different organizations from around the world, and I invite you to be a part of it. It's an open project for everyone. Now, the Genome Project-write was immediately, we were accused that we were going to make designer babies. Absolutely not true. We're not. That's not our goal. Our goal is to be able to write large genomes. But I want to be clear, we're getting to the point where we will be designing our babies and other life forms because the tools are coming. This is IVF, in vitro fertilization. It has given rise to over 8 million babies since the first one was done. Here, a micropipette injects an egg and puts in a single sperm. You can think of this as porn for cell biologists. The first test tube baby, so to speak, was born over 40 years ago in July of 1978. The technology was accepted because at the end of the day, you just make babies, and babies we accept. This is one of my babies, Rosalind. I don't know which embryo made her, but she turned out pretty well. This is my son, Darwin. He's 1 year old last week. He was riding the forward edge of this technology. He was completely genetically profiled before implantation. And he's just the start of a wave of other humans. Because now we have things like CRISPR and genetic surgery, being able to repair genetic damage in a cell right there in the fertility clinic. We're also learning how to do cell biology and take stem cells from our bodies and make eggs. We've done it with mice. People are trying to do this for human. And the ramifications here are significant because what it means is that IVF won't be an expensive procedure anymore. It'll be $500. And you can have as many eggs as you want. And of course, we're moving to a time in the very near future, probably within a decade, when we'll have the capabilities of synthesizing whole human genomes. This is incredible. Programming life is arguably the most powerful technology humanity has ever created. It really has the potential to change our entire world. I don't want to oversell this. This is a living world. This technology will help us live in more dense urban settings because it will literally allow us to grow things that we need. It'll help us clean up a world that is becoming increasingly polluted with older technologies. It'll help us grow the food we need to feed 10 billion or maybe even 100 billion people. And it will certainly help us be take care of the babies, the 90 million or so that are born every single year. Some believe it'll even help us get into space because, of course, if we go to space, we're subjected to a really extreme environment. How do we re-engineer ourselves to better adapt to that environment? Or maybe even on Mars. All I know is the ability to program human life is coming not just to a select few, but to everyone. And that means we're going to have an incredible diversity of humanity springing forth in this century. Darwin is an amazing scientist. He taught us so much about evolution. But I want to be clear, we've moved past Darwin. We're moving into an age of intention where we need to have more empathy for humanity than ever before. It's uncharted waters. It's not just going to be done by a select few. It's our responsibility as a species to understand this and do it right. Just know that there's no way to stop it because even evolution appears to evolve. There's never been a better time to really start doing this. We're connected as a species now through our digital technologies. This will bring us forward into a future that is unimaginable. Thank you.